Hi everyone, welcome to What's Up Physics. I'm Aishwarya, and this is part 2 of our motion in 2 dimensions lesson, where we'll be going over some practice problems. Now, these ones are definitely more conceptual, so they're closer to the style of AP problems, especially those MCQs, and so they're pretty important. If you want to find part 1, which is about going over the concepts and doing some examples, the link will be in the description box below. Alright, let's get into it. Okay, example number 1. Bob jumps horizontally off a cliff at speed v and lands x meters from the cliff in the water. He then jumps again, this time at a speed of 5v. How many meters from the cliff does he land this time in terms of x? Okay, so right off the bat, we see this phrase, jumps horizontally off a cliff. Now, what does this mean? This means that this velocity, this starting velocity right here, is purely horizontal. He has no starting vertical velocity. It's 0 meters per second. Okay, so I want to analyze Bob's vertical motion in both scenarios. So in both scenarios, he jumps from the same height. He covers the same change in displacement. In both scenarios, he has a starting vertical velocity of 0 meters per second, and he has an acceleration of negative 10 meters per second squared. So what does this mean? This means that the time it takes for Bob to hit the ground in both scenarios is going to be the exact same. And we can see that if we look at this third kinematics equation right here. This change in displacement vertically is the same, this initial velocity is the same, and this acceleration is the same as we established. So this time has also got to be the same. And this makes sense because in both scenarios, Bob's vertical motion is just akin to free fall, falling from the same height both times. Okay, so now let's take this newfound information and apply it to our horizontal dimension. Bob takes the same time in both scenarios to hit the ground. And we know that there's no acceleration in the horizontal dimension. So what this means is, just like we saw in the last problem, we can just use this equation to demonstrate or to exemplify the horizontal dimension of Bob's motion. And why? I'll show you one more time. In the horizontal direction, plus 1/2 at squared, in the horizontal dimension, there's no acceleration. This is 0. So this whole term here just cancels out, and we're just left with this change in x is equal to VOT, which is the same equation as this. Now, let's say that this equation represents Bob in the first scenario. He jumps with a speed of v initially, and he lands a displacement of x away from the cliff. Now, in the second scenario, he jumps at a speed of 5v. His time is the same. So in order for his time to be the same, what must we do to the left side of the equation? We also have to multiply that by 5. Because as we learned in algebra, to keep this number the same, we'd have to multiply both sides by the same constant, 5 and 5. Therefore, the second time he jumps, Bob lands 5x meters away from the cliff. Okay, example number 2. Bob stands on a platform with 2 identical balls in his hand. He lets go of them at the same time, dropping one straight down and launching the other horizontally off the platform. Which ball hits the ground first, and which hits with a higher speed? So think about this for a moment. Okay, so although the second ball has an initial horizontal speed, that has no effect on the ball's vertical path as we learned before. This ball, although it has this speed right here, since we see the key phrase that it's launched horizontally off the platform, that means it has 0 vertical velocity to begin with. Since this ball was dropped in free fall, this one also has 0 vertical velocity to begin with. So, what does this mean? This means that both balls' vertical paths are the exact same. They travel the same displacement, they start with the same vertical velocity, and they both have the same acceleration. So their motion in the vertical dimension is completely identical. What does this mean? This means that they both hit the ground at the same exact time. You might be wondering, and this is the most common misconception, since the ball covers extra displacement horizontally because it was launched out, why doesn't it hit the ground later? It's covering more distance. Now, this is a valid question, but the answer to it is that since this ball has this original horizontal velocity that is constant throughout, that velocity makes up for the extra displacement that it travels. This ball over here, it travels no horizontal displacement, but it also has no horizontal velocity. The fact that the second ball has that horizontal velocity allows it to cover that extra displacement in the same time that the first ball just falls to the ground. Now this brings us to the next question. Which hits the ground with a greater magnitude of velocity? Now let's draw this out. While, as we discussed earlier, the first ball has some magnitude of velocity pointing down, the second ball has that same exact final velocity pointing down, because again, the motion in the vertical dimension is the same for both balls. But this one, it also has this horizontal velocity that's been constant throughout. So this ball's final velocity is this resultant right here. Now, if you remember your geometry, the hypotenuse of a triangle is going to be greater than the value of either of its legs. So this value over here, this resultant velocity, is going to be greater than just this vertical velocity, which is equal to this one's final velocity. So the second ball hits the ground with a higher speed because it has that resultant combination of both vertical and horizontal, whereas this first ball is just solely vertical velocity. Okay, example number 3. This is another kind of trippy one. An object is launched from the same cliff thrice, which means it's launched from the same height. Once 45 degrees below the horizontal, once released straight down in free fall, and once 45 degrees above the horizontal. Now the initial launch speed of the first and third scenarios is equal. In which scenario does the object have the greatest magnitude of velocity right before it hits the ground? Assume no air resistance. Okay, so right off the bat, in the first and third scenarios, the object is launched at an angle, and so it has some initial vertical velocity. But in the second scenario, the object is just released into freefall, which means it doesn't have any initial vertical velocity. So we can eliminate this right off the bat because it starts with no velocity, whereas these two start with some velocity. Now, just thinking about it, you might immediately want to pick the first scenario as the fastest because the object is thrown down. It's thrown downwards with some velocity. But in the third scenario, if we draw this third scenario out, eventually when it comes back to the same height at which it was launched, it's going to have a velocity that is equal in magnitude to its starting velocity. Now, what does this mean? Since the problem says that the magnitude of the starting velocity for both the first and third scenarios is the same, this velocity over here, when the object comes back down to the same height, is actually equal to this velocity in the first scenario. Basically, this third trial is going to mirror the first one, just some time later, after it travels this whole path. Therefore, the object will hit the ground equally as fast in both the first and third scenarios. The only difference is that in the third scenario, the object takes more time to hit the ground because it's thrown up, it goes through this whole path, and then it comes to this point in time that's equal to this point in time over here. Okay, number 4. A cannon launches a ball into the air. Which of these claims about the ball's motion are false? A. The acceleration of the ball is the same at all 3 points. B. The speed of the ball is greater at point C than at point A. C. The ball is at rest at point B. And D. All of these statements are true. So think about that for a second. Okay, so you might immediately be inclined to pick D, but that's wrong, and I'll show you why. So let's go through each of these points. A. The acceleration of the ball is the same at all 3 points. Now this is true. Acceleration due to gravity is this small g, is a constant on each planet, and it depends on each planet's mass and radius, and we'll get into that later in physics. So no matter what planet this is on, let's just pretend this is on Earth, because it probably is. If a projectile is in the air, it's always going to have that constant acceleration of negative 10 meters per second squared. This doesn't change regardless of where the object is in its motion in the air. So that's true. Now B, the speed of the ball is greater at point C than at point A. Now this is also true because at point A, it's higher than point C. So it's going towards that momentary rest up here. Whereas this is already past the height of point A, and it's going to be gaining, that's so weird. It's going to be gaining speed as it goes more and more negative because acceleration. So this one's speed, vertical velocity, might look something like this, whereas point C's vertical velocity is going to be a lot greater. So this one is true. Now, answer choice C. The ball is at rest at point B. Now, this is where some people might trip out. At point B, the ball is at rest, vertically. However, since it was launched at an angle, it had an initial horizontal velocity. It has this initial horizontal velocity. And since we know that there's no horizontal acceleration, that velocity is going to be constant throughout the ball's motion. It's going to be constant throughout the ball's motion, including up here. So although we understand that there is momentary rest up at point B, that's only vertically. The ball is still going to be moving in this horizontal direction. It's still going to be moving with that horizontal velocity. So the ball is not at rest at point B. This is a false statement, so C is the correct answer. Alright, that was the end to this video and our kinematics unit in general. Our next video is going to be Intro to Forces, which is, you guessed it, a part of the Forces unit. Thank you for watching us throughout your kinematics journey. Be sure to please like and share our videos if you found them helpful. And see you next unit. Bye!